Welcome to qnawire.
In this exercise, we have a marble that has a mass of 20 grams and is launched from a height of 25 meters, and after that it falls freely to the ground. And we want to know by which distance you miss the target if you're the person who's throwing the marbles in the target on the ground, if you're aiming for the highest precision that you can possibly achieve. Okay, so the first information that we are gonna need in this, in order to solve this question, is the time it takes for the marble to fall to the ground. And remember that according to Newtonian mechanics, the time is just the square root of 2 times g times the height. Okay, so this is the time. I'm not gonna substitute the numbers just yet. So let's calculate the uncertainty in the position, the final uncertainty in the position given the initial uncertainty in the position. Okay, so we know that we have that the final uncertainty in the position of the marble is equal to the initial uncertainty in the position plus the uncertainty in the x component of the speed times t. This is just the equation for a uniform motion in the x direction. Notice that there are no forces in the x direction, and you're aiming for the highest precision. So you want delta xf, the uncertainty in the x direction, to be minimum. So if you want this to be minimum, then we have to differentiate it. And I'm going to differentiate it with respect to delta xi, and we want this derivative to be 0. Okay, then we're finding a minimum of the uncertainty. Now notice that according to Heisenberg's uncertainty principle, we have that delta xi times delta vx is greater or equal than h bar over 2. And since we're aiming for highest precision, I'm going to just consider the equality. Delta xi times delta vx is equal to h bar over 2, which is h divided by 4 pi. So delta Vx is equal to h divided by 4 pi. Actually, there's an m here. I'm sorry for that. Delta Vx is equal to 4 pi m times delta xi. Okay, and the m appeared here because actually Heisenberg's uncertainty principle tells us that delta xi times delta px is greater or equal than h bar over 2, and the momentum is m times the speed. And I'm assuming that the mass is known. So notice that delta xf is equal to delta xi plus ht divided by 4 pi m delta xi. And now we can differentiate this with respect to delta xi. So this is 1 minus ht divided by 4 pi m delta xi squared, and we want this to be 0 so that the function is a minimum. So you get that delta xi is equal to the square root of ht divided by 4 pi m. Okay, and now we can substitute this back into delta f and the delta xf equation. So we have that delta xf is delta xi, and that's the square root of ht divided by 4 pi m plus ht divided by 4 pi m times delta xi. So that's the square root of ht divided by the square root of 4 pi m. So you get that this is equal to 2 times the square root of ht divided by 4 pi m which is the same as just the square root of ht divided by pi m. And now we can substitute the numbers. First, before substituting the numbers, just notice that t is the square root of 2gh. So delta xf, that is the minimum uncertainty in the final position of the marble, is equal to the square root of 6.63 times 10 to the minus 34 joules second times the square root of 2 times 9.8 meters per second times h, which is 25 meters, divided by pi times the mass of the marble, which is 20 grams or 0.02 kilograms. So delta xf is equal to 4.83 times 10 to the minus 16 meters. So this is how much you miss the target horizontally.